Good evening, ladies and gentlemen, and it's been a long time since I put out a video, and it hasn't been for lack of trying. I've had a couple of ideas that I thought were hot S-H-I-T, and they ended up being not so good. So a lot of footage got thrown in the garbage. I don't want to spoil the ideas because I think they're good, and I haven't given up on them completely. One is related to a workflow with a certain type of processing that I think might really work out if I can get it to work. And the other one was some equipment stuff that I thought I had figured out. None of it is working, and I'm tired of fighting with it, so I'm just going to put those ideas on the shelf for now and get back to doing what I love and what I know you love, astrophotography. I've got the 9.25, the 0.7 reducer, the 2-inch Optolong L Pro, and a full spectrum 7D Mark II ready to go for this evening. But somebody said that they wanted me to talk about focal length and focal length selection, what it means to our astrophotography, because it can be kind of a confusing subject for a beginner. So we're going to talk about focal length. Focal length, put simply, is just the distance that it takes your primary objective to bring your light to focus, right? To converge your light rays. So, you know, if you've got a 400 millimeter focal length, that means from the front of your optic, you know, if it's a refractor from the front of that lens, or a reflector from your mirror, then it takes 400 millimeters to bring that light into focus. The easy way to remember it is just to think of it like you're looking through a hole. If you're up close, you know, you can see a wider field of view than if you're far away. So the longer your focal length is, the smaller the section of the sky or whatever you're looking at is. A lot of the bigger targets in the night sky, like the Andromeda Galaxy, for example, or if you say you want to frame up the Heart and Soul Nebula in the same frame, you need a pretty short focal length, like 100 or 200 millimeter focal length. But if you're taking pictures of Jupiter, for example, you want like a 4,000 millimeter focal length because you're looking at a really tiny section of sky. So how that relates to your field of view is that your field of view is a combination of your focal length and your sensor size. Your optical tube is going to produce an image circle based on, you know, its aperture and its focal length and its design, and then in that image circle, how big your sensor is, how much of that image circle you fill up, will determine your exact field of view. It's not stuff you need to memorize because there are tons of apps. I use Sky Safari on my phone, and you can input your focal length and sensor size, and it will put a square on the screen, the size of your field of view, and then you can just, you know, look around and look at targets and see what you're going to fit in your frame. So that's really handy. So if you're deciding on your focal length for your telescope, for your first telescope, or maybe your second or third or fourth or 10th telescope, it's best to decide what your long-term goals are. Put that stuff in your planetarium program and just kind of look around and see what you're going to fit in your frame. And that'll help you make up your mind as to how long of a telescope you want. And you know, if you do want to do really wide field stuff, you know, you might not even want a telescope. You might just, the Samyang 135 millimeter lens is a real popular lens for astrophotographers. It's very sharp. It's a high quality lens for astrophotography. A lot of people just use, and I've got some shots with my 100 to 400 Canon L zoom lens. That's a real nice range of a focal length. Tonight I'm going to be shooting a chunk of the Pelican Nebula with the reducer on. That one part where it's got that little dust pillar sticking out, I think that looks pretty interesting. But this weekend I'm going to try to get like 10 hours on that. I was supposed to have some guests over who wanted to learn about astrophotography, but they are a day late. Hopefully they're here tomorrow and we can talk about the workflow. Alright, so over the last 3 days I got about 10 hours of integration. I was hoping to get about 15, but you know, clouds played a major role in that. 10 hours isn't bad. So we're going to go ahead and go through and process this. Now I did this with Deep Sky Stacker with my friend who was over here just to show her how the workflow goes for post-production on this data, and it did not go well. Because I have multiple nights, and I don't think Deep Sky Stacker handled the grouping well. So we're going to go ahead and use weighted batch pre-processing. Now I've got 2 different sets of flats that need to be applied to different nights because I moved the camera. So I'll show you how we do that. Weighted batch pre-processing. You go to add custom files, and then you give it assign it a filter, and it will group the flats together. Why is this taking so long? Open up. Okay. Reset all parameters. Okay. So these will be CFA images. Okay, so bias, add bias. Add darks. Now these are going to be the 300-second (86°) darks. Now when we add our flats and bias, or our flats and lights, we'll go to add custom. Now let's put the first set of lights in as N1. Add files, Astro, Pelican detail. So this will be our first set of lights. N1. Add custom, we'll put our first set of flats in. Filter name N1. The 6th, okay. First set of flats. Okay, now let's put our second set of lights in. Whoops. Okay, those are all of our lights. Now we'll add our second set of flats. Okay, that's our second set of flats. So we got N1, N2, lights, N1, there should be 30 of those and about 70 of N2. Okay, that looks good. Make sure our darks are good. This should not be here. Okay, this all looks good. No, we don't want to calibrate, only generate. Now we want, I think, yeah, let's just use this one as a registration frame because okay, image registration data. I'm going to give it one tick of noise reduction here. That always helps me with my image registration. Okay, set our output directory to my SSD there. Registration, rejection maps. Okay, let's run it. Yeah, thanks. Weighted batch pre-processing just finished going through the subs. Now I'm gonna go blink through and make sure we didn't keep any garbage in there. I really need to figure out why my mount does that. I think it might have some junk in the gears or something. It might be a software problem. Could be anything really. Alright, other than that, it looks pretty good. Go ahead and release the memory. Open up image integration. Just use everything standard and then linear fit clipping. Just finished integrating all those subs. I'm sure it's garbage. Ew. Might have to be a problem with my flats. No, that looks pretty flat. Not bad. Not bad at all, really. Okay, so this was just over 9 hours of integration. I was hoping to get 15, but you know how that goes. Yeah, it looks good. So we'll go with this. I'm going to save this. Why is it defaulting to JPEG?
Papa?
Yeah, baby. Hi. Look at this is the part of the Pelican Nebula we just finished integrating. Okay, so I'm going to give you a quick run through of how I use Starnet in my workflow. And I'm going to put a link in the description on a way to get Starnet to run on your GPU, because that is a game changer. You know, it used to take a couple minutes, now it takes like 20 seconds to run Starnet. So the first thing I'm going to do is crop out all of the stacking garbage. In the corners.
Hey, why was this in my toes?
I don't know, sweetheart.
Why was this in my toes?
Okay, now we will try to neutralize this background because there's a little bit of a gradient in there. Making sure we get it up around the edges and Violet. See, I don't know if I should select this as background or not because it's not quite background. We'll try it. Hope it doesn't clip that out. Okay, now let's try this. Did our 4-year-old just ask for ibuprofen? Yeah. Why do you want ibuprofen, Violet? Okay, that kind of works. Not great. Let's try and relax this a little bit. No, that made the corner look bad down there. Wonder if we can probably go put a few samples down here. This is pretty dark. Okay, let's try this. Oh, that looks pretty good. Alright, so we'll go with this.
Daddy.
Let's go ahead and close this. What, sweetheart?
I'm hungry again.
Again?
Yep, I want some eggs.
Well, we're not going to have eggs right now.
Can we have eggs for lunch?
Okay. No, we're going to have some leftovers for lunch. We got some enchiladas to eat up. So now we will go and... Okay, that's done. Now, let's just go ahead and give it a quick stretch. Okay, image is stretched. Now I will... The color balance already doesn't look that bad, so I'm not that worried about color calibration. I'm going to use Starnet. And remove the stars. So we will clone this.
You're gonna clone it?
Yeah, we cloned it. Let's
Well,
call it.
what does that even mean?
It means we copied it. Now we'll run Starnet on it and pull the stars out of it. It probably isn't going to mess with this really big one. But yeah, follow the link in my description and go do all the steps to get Starnet to run on your GPU. It'll really speed things. If you have an Nvidia GPU that can run CUDA, I think. There are a couple requirements, but if you meet the requirements, then by all means you have to go get the Starnet to run on your GPU. Because it really speeds it up. Right, Violet? Okay, so here is our starless image. Looks pretty dang good. Now what we do is open up Pixelmath. And we want the stars on their own. So we will subtract the starless image from our background extracted image. Make sure it's on create new image And that's probably all we need to do. Now these are our stars. Pretty simple. Now what I do, they're always a little bit weird looking, like grainy like this. So I go, let's make a preview to work with. Go and open up multi-scale linear transform, and we can actually subtract, go into negative territory on the detail layers, and it will blur the stars a little bit to make them look a little smoother. It really makes them look better. Okay, that looks pretty good. So we'll go ahead and run that. And that'll smooth out the stars. So that's what they used to look like, all grainy and nasty. We dropped the bias layer on them and they're smoothed out now. Now let's hit these with a little bit of saturation. That looks pretty good. Okay, so the stars are ready. So let's go ahead and save these. Let's go ahead and change this to stars. So it's easy to find in Pixelmath. Okay, stars are ready. Now we will work on our nebula. Now the first thing we want to do, I think the first thing I'm going to do is noise reduction on this to smooth it out. We'll go back to multi-scale linear transform. Let's make a preview to work with so we can see what it's doing. And start hitting the noise reduction here and see what happens. Second layer, that's probably enough. I wonder if we try to sharpen that at all, what happens. Not good. That looks pretty good. See, so this is the original, and then these are our wavelet transforms to remove the noise. It's pretty good. We'll go with that. All right, now we're going to stretch it to bring out the detail in the nebula, but we need to protect this bright star because that's going to be a big mess if we don't protect it. So we'll go to mask generation, range selection. We want it just to get rid of the nebula. Maybe leave a little bit, but we also want it we want to really crank up the smoothness because we don't want a big gradient on that stretch. It's probably pretty good right there. So now this will, I don't know why I do that backwards every time. But anyways, okay, that will protect that star while we stretch the nebula a little bit. Let's go to curves, transformations. increase the contrast. Yeah, that star still looks pretty good. That's looking pretty good. What if we boost up the red a touch? I think that looks pretty good. Okay, now just for the sake of brevity, I'm just going to go ahead with this because I don't want to hold you guys up. I might go back and monkey around with this a little bit more. But now we will just disable the mask and take Pixelmath and add our starless plus, whoops, not equals, plus our stars, and that will give us our image. And there you have it. Now I'm probably going to go and touch this up a little bit, but you know, even when you zoom in a lot, there's a little bit of artifact there, but I love this Herbig Haro object right here. That is so cool. I need to get more integration on it to pull it out better, but that's cool. Like that's literally the birth of a star, and it's really neat to see it. Yeah, the noise is not great here. I might try to get more integration on it. Like, is this dust or is this bad darks? I don't know. It's so hard to tell. I think that's dust. I think that's a legitimate thing. But anyways, yeah, there we have it. And I am happy with the way you can still see, if you really zoom in, there's a little bit of pixelation left in those stars. But hitting it with multi-scale linear transform really improved the way the stars looked. And the star color is good. And yeah, I'm happy with this. So we'll call that a win. Alright, now we'll do a segment in which we answer an astronomy question. This one comes from one of our users. Please, could anyone tell me if there is evidence of probes with sophisticated equipment for deep space relay in action? Must be possible, because what with Neowise being in our orbit and not the first time either, I know they landed before, but what about must be able to attach and relay back to us? If we can stand on rock here and observe, we must be able to. Be well, grateful for input.